Standard Deviants present The Deep-Fried World of Organic Chemistry.
A long time ago, when organic chemists first began to play around with these compounds, all of these strict naming rules hadn't been invented yet, so they just sort of winged it. And, well, those names have been around for so long that when someone actually did try to come up with the strict naming rules, everyone just said, hey, why fix it if it ain't broke? So they just let some of those names stick. And that's how we got isobutane.
Isobutane is the common name for 2-methylpropane. It sort of makes sense, right? Because all they're saying is that isobutane is an isomer of butane. Of course, by today's standards, this molecule is called 2-methylpropane. But we can basically guarantee that you'll come into contact with the name isobutane, so you'd better know it.
Let's look at butane again. Like we said, when an alkane loses a hydrogen to bond to something bigger, we drop the ane ending and change the name to alkyl. And here's where things get tricky. We've assumed that the hydrogen that's getting kicked off is one of the hydrogens on the end of the butane chain, and we've named the leftover alkyl group butyl accordingly. But what if a hydrogen gets knocked off of carbon 2? Is the name still butyl? Nope. And we kind of have to have a long discussion to figure out what we do call it. So find the remote. Sit tight. Here's where the R's come in.
Do you see this carbon here with one R and 3 H's attached to it? Well, what that's telling us is this carbon is attached to one other alkyl group. Remember, an alkyl group is just an alkane that's lost a hydrogen in order to bond to this carbon. R is a shorthand for an alkyl group, just like the atomic symbol C is shorthand for carbon. So the R just tells us that there's an alkyl group there, and that tells us that there's a carbon there. That alkyl group could be methyl or ethyl or propyl or any other alkyl group. We don't know, and we don't care. All that's important is that we know that the R there is telling us that there's a connection to a carbon there.
And H just means hydrogen, of course. So, this carbon here with one R and 3 H's is attached to one other carbon and 3 hydrogens. We call this type of carbon a primary carbon because it's only attached to one other carbon.
And now, check out this carbon with 2 R's and 2 H's. That lets us know that our carbon is attached to 2 other carbons and 2 hydrogens. We call this type of carbon a secondary carbon. And this carbon here, with 3 R's and only 1 H, is called a tertiary carbon because it's attached to 3 other carbons. Finally, this carbon here, with 4 R's attached to it, is called a quaternary carbon. Got it? Primary, secondary, tertiary, and quaternary.
Primary, secondary, tertiary, quaternary.
The shorthand for primary is a 1 with the degree superscript. The shorthand for secondary is a 2 with the degree superscript. The shorthand for tertiary is a 3 with the degree superscript. And you guessed it, the shorthand for quaternary is a 4 with a degree superscript.
And the shorthand for Jenny is a J with a degree superscript.
Let's look at butane again. This carbon over here, on the end of the butane chain, is attached to one other carbon, so we know that it's a primary carbon. And this primary carbon has 3 hydrogens attached to it. Those hydrogens are called primary hydrogens because they're attached to a primary carbon. Simple enough.
But carbon 2 in butane is attached to 2 other carbons, one over here on the end of the chain and one over here right next door. Since carbon 2 is attached to 2 other carbons, carbon 2 is a secondary carbon. And yep, you guessed it, the hydrogens attached to carbon 2 are secondary hydrogens. Make sense? Carbon 3 is also a secondary carbon because it's got 2 other carbons attached to it. And the hydrogens on carbon 3 are also secondary hydrogens. Carbon 4, over here on the end of the chain, is a primary carbon again because it's only attached to one other carbon. And the hydrogens attached to it are primary hydrogens.
So, like we were saying, if an N hydrogen is knocked off of butane so that it can attach to something bigger, we change the name butane to butyl. Butane has lost a primary hydrogen in order to do this. But what if butane wanted to knock off a secondary hydrogen in order to bond to something bigger?
Let's say butane kicks out a hydrogen from carbon 2. Butane has kicked out a secondary hydrogen from a secondary carbon, so we can't call it butyl because, well, It's not butyl, it's sec-butyl. That makes a lot of sense, doesn't it? Butyl tells us that a hydrogen is missing in order for the alkyl group to bond to something else, and the prefix sec tells us that it was a secondary hydrogen. Not so bad, right?
Now let's look at 2-methylpropane again, which we told you earlier can also be called isobutane because it's an isomer of butane. The outer carbons on isobutane are all primary carbons because they're each only attached to one other carbon. And, of course, the hydrogens attached to them are all primary hydrogens. But look at carbon 2 in the chain, in the middle of the molecule. It's attached to 3 other carbons, so carbon 2 is a tertiary carbon, and its lone hydrogen is a tertiary hydrogen.
Let's say isobutane kicks out one of its primary hydrogens in order to bond to something bigger. No problem. We would just change the name isobutane to isobutyl. But if isobutane booted the hydrogen from carbon 2, which is the tertiary hydrogen, its name would become tert-butyl.
Hey, where'd the iso go?
Well, there's only one tertiary hydrogen in this whole molecule, and we know that it couldn't come from straight-chained butane, because straight-chained butane doesn't have any tertiary hydrogens. It must have come from isobutane, so we can just call this alkyl group tert-butyl.
Again, that makes a lot of sense, doesn't it? We've just kicked out a hydrogen, so we just changed the name isobutane to butyl. And the hydrogen we booted was a tertiary hydrogen, so just add the prefix, tert, to tell everybody that the hydrogen was the tertiary hydrogen.
So we've got butane, butyl, and sec-butyl, and we've also got isobutane, isobutyl, and tert-butyl. You're just going to have to learn these suckers, and you can find them on your standard deviance insert card.
There's only one more of these that we have to know, and it's got something to do with propane, our 3-carbon chain. This one's actually easier than the ones we just looked at.
Propane has 2 primary carbons, one on this end of the chain and one on the other end. When propane loses a hydrogen from one of these primary carbons, we just change the name propane to propyl.
This carbon in the middle of propane is a secondary carbon because it's attached to 2 other carbons. This is the only other type of carbon in propane. It's the only secondary carbon we'll find. If one of the secondary hydrogens is removed from the secondary carbon, we get an isomer of the propyl group. So all we do is call this alkyl group isopropyl. What could be easier?
Okay, it's time for a mini review. And then we have to figure out how to name bigger alkanes. So here we go.
If an alkane loses a hydrogen in order to bond to something else, we drop the A-N-E ending from the name of the alkane and add YL. If a central carbon is attached to one other alkyl substituent, or one other R group, we say that that carbon is a primary carbon. If a central carbon is attached to 2 other carbons, it's a secondary carbon. To 3 carbons, it's a tertiary carbon, and to 4 carbons, it's a quaternary carbon. The hydrogens attached to those carbons are primary, secondary, and tertiary hydrogens, respectively. Propane is an alkane with 3 carbon atoms. When propane loses a primary hydrogen to bond to something bigger, the name changes from propane to propyl. On the other hand, if propane loses a secondary hydrogen, the group's name changes from propane to isopropyl.
Butane has 4 carbons. If butane loses a primary hydrogen, its name becomes butyl. If butane loses a secondary hydrogen to bond to something bigger, its name becomes sec-butyl. 2-methylpropane and butane are isomers. Isomers are different compounds that have the same molecular formulas. The common name for 2-methylpropane is isobutane. When isobutane loses a primary hydrogen in order to move on to grander things, its name changes to isobutyl. But when isobutane loses its one and only precious tertiary hydrogen, its name goes from isobutane to tert-butyl. And that's it.
All right, we've covered a lot of ground there. Why not go get some fresh air? When you come back, you'll feel all refreshed, and you'll be ready to dive headfirst into naming bigger, more complex alkanes.
Right. Now let's try to name a bigger, more complex molecule. Obviously, there's a lot more going on here than in the straight-chained alkanes we just looked at. This molecule is an alkane. It consists of only hydrogen and carbon, and all the bonds are single bonds, but it's a branch chain alkane. To name alkanes of this size, we have to follow a few simple steps.
The first step in naming an alkane is to find the longest continuous chain of carbon atoms in the molecule. This is trickier than it sounds. You want to make sure that you're counting the chain with the most carbons. There may be several pathways that you have to look at first to find the longest chain. Don't let the branching chains confuse you. Let's look at our molecule as we've written it.
The long horizontal straight chain through the middle of this compound has 5 carbons. This chain has 6 carbons, so this could be the longest chain, but we have to be sure to check out all possible pathways, and we have to be sure we're including the branches. This chain has 7 carbons and is the longest continuous carbon chain. The longest chain in a compound is called the parent chain. This parent chain is a 7-carbon alkane, so we name it heptane.
After you've named the parent chain, you have to number the carbons in it. Following step 2, start numbering at the carbon closer to the first branch point. In other words, we want the branch points to have the lowest numbers possible. We'll explain. Let's go back to our heptane molecule.
Oh, come on. Where are you? There we go. Oh, shoot. Come back here.
This heptane has 2 different branches. Do you see them highlighted here? If we start numbering from the right on the long carbon chain, the first branch point will be at the 4th carbon, and the second branch point will be at the 5th carbon. If we start numbering the main chain from the left, the first branch point is at the 3rd carbon, and the second branch point is at the 4th carbon. See, the deal is to number the suckers so that the branches have the lowest number possible.
Okay, so we've named and numbered the parent chain, and now we also have to name and number the branches. We're going to start referring to the branches as substituents, just like we did when we spoke of substituents bonded to a central atom.
We name the substituents, or the branches off of the main chain, exactly as we would name the main chain, by counting the number of carbons. This heptane has 2 substituents. The first, which is bonded to the number 3 carbon, is CH3. It only has 1 carbon, so we know it must be some sort of methane. It only has 3 hydrogens, though, and this tells us that this methane has lost a hydrogen so that it could bond to the parent chain.
We told you earlier that an alkane which loses a hydrogen is an alkyl group, and the correct name for this alkyl substituent is methyl. The methyl is attached to the parent chain at the 3rd carbon, and if you remember, when naming the alkyl substituent, we told you that you have to include the number of the carbon that the substituent is attached to on the parent chain. So, since this methyl group is attached to the parent chain at carbon 3, we name it 3-methyl.
The second alkyl substituent has 2 carbons, so it's ethyl. The ethyl is attached to the 4th carbon, so we call this substituent 4-ethyl.
After all the work we just did, we know that we have a parent chain, heptane, with 2 alkyl substituents, 3-methyl and 4-ethyl. When we name the molecule, we put the alkyl substituents first, all separated with hyphens, and then we add the name of the parent chain. Let's start with the substituents. If you have more than one substituent, as we do here, you alphabetize them and separate them with hyphens. Then you add the name of the parent chain. Voila! This molecule is 4-ethyl 3-methyl heptane.
Amendment to step 3. If there are 2 substituents attached to the same carbon, we assign both of them the same number.
Being able to name molecules is a fundamental of organic chemistry. So let's try one more.
Step 1. Determine the parent chain, the chain with the most continuous carbons. In this case, the longest chain is a 9-carbon alkane, nonane.
Step 2. Number the carbons beginning with the carbon nearer the first branching point. We should point out something pretty important here. There are 2 initial branching points on the 3rd carbon in the chain, whether we're moving from left to right or right to left. What do? Figure out which branching point is closer to another branching point.
Counting from left to right, there's a branching point at carbon 3, and then not again until carbon 6. Counting from right to left, however, the first branching point is at carbon 3, and the next branching point is at carbon 4. We'll number this nonane from right to left.
Step 3. Identify and number the substituents. There are 3 alkyl substituents attached to this nonane at the 3rd, 4th, and 7th positions. The alkyl substituent at carbon 3 has 2 carbons, so we name it 3-ethyl.
The alkyl substituent at carbon 4 has 1 carbon, so we call it 4-methyl. The alkyl substituent on carbon 7 also has 1 carbon, so it's 7-methyl.
And finally, let's put it all together. We have a parent chain, nonane, with 3 alkyl substituents, 3-ethyl, 4-methyl, and 7-methyl. We write the substituents in alphabetical order and separate them with hyphens.
2 of the substituents are methyls, but we don't want to write them twice. That would be way too wordy. Instead, we'll use a prefix to indicate how many methyls we have. In this instance, we'll use the prefix di because there are 2 methyls. If there were 3 methyls, we would use the prefix tri. And if there were 4 methyls, we would use the prefix tetra. So in this instance, the 2 methyls become 4,7-dimethyl.
There are a few little extra rules you have to follow that we should mention here. Use commas to separate numbers, and use hyphens to separate numbers from the substituent names. Also, we told you that when there are 2 or more substituents, you should alphabetize them. When you use prefixes such as di or tri, however, alphabetize the substituents by the main name of the substituent, not by any prefixes the substituents may have.
And finally, the name of the compound is 3-ethyl 4,7-dimethylnonane.
Okay, so now we know how to name alkanes with long carbon chains. But sometimes the carbons of a molecule will be arranged in rings instead of in long chains. What then? If the carbons of an alkane are arranged in a ring, we call that alkane a cycloalkane.
It's in a ring, so it cycles. See? Cycloalkanes. See ya!
Cycloalkanes are rings of CH2 units. The basic formula for a cycloalkane is CnH2n. As usual, N equals the number of carbons in the molecule. Naming these cycloalkanes is really easy. Remember all those names we just learned for chains of alkanes? Propane, butane, pentane? Well, those same names are going to apply here, only we're going to add the prefix cyclo.
For example, a ring with 3 carbons is cyclopropane, a ring with 4 carbons is cyclobutane, and a ring with 5 carbons is cyclopentane. Cyclopropane!
Cyclobutane! Cyclopentane!
By far, the most common cycloalkane is the 6-carbon ring cyclohexane. Remember it, nature loves it.
When you draw a cycloalkane, a good shorthand that chemists use is simply to draw a polygon. A triangle for cyclopropane, a square for cyclobutane, a pentagon for cyclopentane, a hexagon for cyclohexane, and so on. You don't even have to include atomic symbols when you draw simple cycloalkanes, because we've already told you that each corner of whatever polygon you just drew will contain a CH2 unit. But don't forget, unless something is specifically written in on one of the carbons, there are 2 hydrogens there.
Just a little while ago, we looked at straight-chained alkanes with alkyl substituents. These substituents were alkyl groups because they themselves were alkanes which had lost a hydrogen in order to attach to the main chain alkane. Cycloalkanes are no different. They can have alkyl substituents as well. Organic chemists call these cycloalkanes with alkyl substituents alkyl substituted cycloalkanes to indicate that the main component of the molecule is a cycloalkane and that this cycloalkane has at least 1 alkyl substituent. Real quickly, let's name some alkyl substituted cycloalkanes. There are only 2 steps to naming cycloalkanes. Step 1. Count the number of carbons in the cycloalkane ring and count the number of carbons in the largest substituent. If the cycloalkane has more carbons than the largest substituent, we would name that molecule a cycloalkane with an alkyl substituent. But if the largest substituent has more carbons than the cycloalkane, we name the molecule as an alkane with a cycloalkyl substituent.
Do you see the difference? The wording and order are important because they indicate which component of the molecule is the main component. Let's look at an example.
Step 1 says we should count the number of carbons in the cycloalkane and then count the number of carbons in the largest substituent. This ring has 5 carbons and is therefore a cyclopentane. Its alkyl substituent has 1 carbon and is a methyl group. Groovy. So we've got a methyl group and a cyclopentane. This cycloalkane has more carbons than its substituent, so this molecule is an alkyl-substituted cycloalkane, and we have to name it accordingly. We would name this molecule methylcyclopentane.
But take a look at this molecule. The cycloalkane has 3 carbons. The largest substituent is an alkane with 4 carbons. The largest substituent has more carbons than the cycloalkane, so the substituent is actually the main component, and the cycloalkane is its cycloalkyl substituent. In other words, this molecule is a cycloalkyl substituted alkane. The cycloalkyl substituent has 3 carbons, so we name it cyclopropyl. The main alkane has 4 carbons and is butane. Put it all together and we have cyclopropyl butane.
But we're forgetting one thing. This molecule is just an alkane sporting a cycloalkane. In step 2, we'll learn how to number the carbons of a cycloalkane. But we already know how to number regular old alkanes.
Because the alkane is the longest continuous chain of carbons, we number its carbons at the end nearest the first branching point. So we would number this butane at the end near the cycloalkyl group. This molecule is 2-cyclopropylbutane because it has a cyclopropyl substituent attached to the second carbon of the larger butane component.
So basically, we named this cycloalkyl substituted alkane exactly the same way we just named regular old alkanes. Only this time, one of the substituents was a cycloalkyl group. Piece of cake, right?
So, in step 1, we figured out whether our molecule was an alkyl-substituted cycloalkane or a cycloalkyl substituted alkane. But we still don't know how to number the carbons of a cycloalkane. Step 2 tells us how to do just that, to number the carbons of an alkyl-substituted cycloalkane. The last example we looked at was a cycloalkyl substituted alkane. So we were dealing with an alkane with a cycloalkyl substituent. And as we know, when we name alkanes, we number the carbons in the longest continuous chain, beginning with that end of the chain closest to the first branching point.
The same thing applies when the carbons are in rings. When numbering the carbons in a cycloalkane, start at the first carbon that has a substituent attached to it. If there are 2 identical substituents, we number the rings so that each of the substituents has the lowest possible number. Let's look at an example.
The cycloalkane here has 6 carbons and the 2 substituents have 1 carbon each. This molecule is an alkyl-substituted cycloalkane because the cycloalkane has more carbons than the individual substituents. The carbon ring has 6 carbons and is therefore cyclohexane. The 2 substituents each have 1 carbon and are both methyls. Remember, when there are 2 or more identical substituents, we use prefixes, so these 2 methyls become dimethyl. Now all we need to do to put this whole name together is number the carbons. We start numbering at one of the substituents and number around the ring so that the 2 substituents will both have the lowest numbers possible.
In this instance, we'll start numbering at either one of the methyl substituents, and then we'll just continue to number around the ring clockwise, so the 2 methyl groups have the lowest numbers possible. We have a methyl group at carbon 1 and another methyl group at carbon 3. So we call the 2 methyls dimethyl, and all together we call them 1,3-dimethyl. This molecule is 1,3-dimethylcyclohexane.
Notice here that it doesn't matter whether you number clockwise or counterclockwise, as long as the substituents are numbered with the lowest number possible.